don't think we're going to start at 0 if we're going to use the right endpoints. Right? If we're going to use the rectangles that are over estimates, remember I started at 1. That's not 0.1. Let me put it in a different context. Delta x is 5 over n. If I told you delta x was 1, then your first endpoint was 1, right? What if delta x was a half? What would be your first right endpoint? A half, right? What if delta x was a quarter? So a quarter would be 20 rectangles. If we had 20 rectangles, delta x would be a quarter. Wouldn't your first plug-in be 1/4? Okay, let's stay with the 1/4 idea. So the first, x1, we want to be a fourth. What would x2 have to be? A half. What would x3 have to be? 3/4. x4, 1. So you have to come up with a way that you can plug in 1, 2, 3, 4, 5, but where 1 gives you quarter, 2 gives you half, 3 gives you 3/4, 4 gives you 1, 5 gives you 5/4, so on and so forth. But we don't have a quarter here, we have 5 over n. So what I need here is f of, check this out, don't we need 5i over n? Go back to 20 rectangles, n equals 20. If n equals 20, 5i over 20 is just I over 4. And when I equals 1, you get 1/4. When I equals 2, you would get a half. When I equals 3, you would get 3/4. When I equals 4, you would get 1, so on and so forth. That right there, that's the key step. Being able to figure out what do I plug into the function to get the cascading endpoints that I'm using to calculate the height of my rectangles. Because remember, all that is the height of a rectangle times the width of a rectangle. Height, width. So what do we need here? We need the limit as n goes to infinity of the summation of I equals 1 to n of, that's 2/5 times 5i over n squared times 5 over n. And this is the limit as n goes to infinity of the summation of I equals 1 up to n. All right, let's see, what do we got here? We've got n cubed in the denominator for sure. In the numerator we have an I squared for sure. Let's see, these 5's cancel. And looks like we got 25i squared times 2, so 50i squared. Now, this is not a trick question here. Let me cover up the infinity for a second. If you just look at this sum, which one of these two is the variable? Is it the I or the n? I is the one that's changing, right? I equals 1, I equals 2, 3, 4, 5, all the way up to n. So if I cover up the limit, the n here is fixed. So you can factor out the 50 over n cubed. But you can't bring it past the limit because n is supposed to go to infinity. So the proper way to write this is the limit and then factor out the 50 over n cubed, and then you're left with the summation, right? Now, everybody agrees that the area underneath the curve is finite. Yes?
Yes.
It's definitely between 12 and 22, right?
Yeah.
So this limit should exist. Okay. What's my formula for I squared again? Now we're using n, so it's n all over. Now, what's the degree of the numerator? So it's a cubic polynomial, right? It's n cubed is the degree. Look at the degree of the denominator. N cubed. So it's n goes to infinity, is this limit going to exist?
Yes.
You have a cubic polynomial over another cubic polynomial. Isn't that going to have a horizontal asymptote as n goes to infinity? Those of you who did curve sketching in 3.6, you got a cubic over a cubic. That's going to reduce to a real number, right? If it was a fourth degree over a third degree, then you'd end up with an oblique asymptote that's going to go off to infinity. Certainly the area underneath that curve is not infinity. If you had a second degree polynomial over a third degree polynomial, that would go to second degree over third degree, go to 0. Is the area 0? No. So the only way that this works is if the degree of your numerator is the same as the degree of your denominator. So for those of you who like to have places where you should check your work, this is a big one. That the degree of the numerator and denominator should be the same. If they're different and you have a finite area, you lost it somewhere.
So we're basically trying to cancel out the ends.
I would not say we're trying to cancel out the ends. No, n is going to infinity. So let's simplify this. This is now the limit as n goes to infinity. Well, certainly we can get rid of one of the ends, right? 50 over 6 is 25 over 3. And then times, we're going to have 2n squared plus 3n plus 1 all over n squared. Yes? What's the trick? Because if I just go with direct substitution, I get infinity over infinity. So we got to multiply everything by 1 over squared, so it's going to be 2 plus 3 over n plus 1 over n squared all over 1. And as n goes to infinity, this ends up as 25 over 3 times 2, which is 50 over 3, which is, what, 16 2/3, which is right between 12 and 22. And that is your exact distance traveled over 5 hours under that velocity curve. Now, some things here.
What am I getting?
Notice the logic here, that the lower rectangles is less than or equal to the area under the curve, which is less than or equal to the upper rectangles. We got a big theorem here that says let f of x be continuous and non-negative on the closed interval a to b. Then the limit as n goes to infinity of the summation from I equals 1 to n of f of little m sub I times delta x, that would be the underneath rectangles, that would be the underestimates, lowercase m underestimates, would equal the limit as n goes to infinity of the summation of f of big M times delta x. That's the overestimate rectangles. If those two guys are the same, where delta x is going to be b minus a over n, where f of little m and f of big M are the respective minimum and maximum lengths. So it's a fancy way of saying that you got the underestimate rectangles and the overestimate rectangles. Number 2, it says the area bounded by f of x, the x-axis, x equals a and x